everyone. Thank you firstly to the organizers for the opportunity to present today. I will be talking about this paper I put out last year on Axions and their physics in during inflation. Since the physics displayed by them, I think is pretty interesting, and I will particularly have my eye towards a potentially interesting detection channel for such axions. Okay, so let's get started. So firstly, why axions? Well, axions, just to remind everyone, were first invoked to resolve the strong CP problem, which is to explain why the neutron electron dipole moment is so small, or alternatively to explain why the angle between angle subtended by quarks inside a neutron is so small. But they were quickly recognized to also be a useful dark matter candidate, axions or particles like axions or ALPS. And moreover, it was recognized that these particles are actually abundant in theories of quantum gravity. So they're very well motivated for a variety of reasons as particles to look for in nature. Okay, but what do I mean by an axion? So I will adopt its basis definition, which is to say that it's just the field theoretical analog of a particle on a circle. That is, at each point in space, it takes values inside a circle, whose size is parameterized by its so-called decay constant f. So it's an important constant in characterizing the physics of an axion. So such axions, such light effectively massless axions, are abundant in really extra dimensional UV models, where these axions, the decay constant can span a huge range of values, as high as the Planck scale, and this value is controlled by the size of your extra dimension. So these axions carry some memory of this extra dimensional physics. Now, I'll be studying these axions during inflation, which is of course very successful at explaining 2-point statistics of a CMB and large scale structure. And apart from just predicting the 2-point statistics, inflation generically also predicts non-Gaussianities for both of these observables. And the reason is because inflation is generically an interacting theory, so it always contains some base level of interactions. And so, for instance, this could be self-interactions of the inflaton, or exchange processes with some spectator field, which I call sigma over here, that propagates through the inflationary bulk. Okay, so in this context, I could ask, what happens when you exchange an axion, if you have a spectator axion? Just to be clear, the axions I'm referring to would be spectators and not the fields responsible for inflation, although they could be, but that's not the aspect that I will be focusing on. So the two main points that I will try to communicate is that the physics of these axions in de Sitter, or inflation, seems to uniquely care about the fact that these are compact, these have a compact field space, that they're compact scalars, and moreover, because they're light, effectively massless during inflation, that these axions will represent a strongly coupled sector during inflation, and as such, studying them is a departure from studying the kind of weakly coupled free fields that have been studied extensively in the past. Okay, so first let's talk about free fields. Now, free fields in the sitter are labeled not by the mass but rather by the scaling dimension. So if you take the 2-point function of a scalar field and you pull it apart at long distances, it breaks down into these two power laws, where the exponent is what you call the scaling dimension, and the other one, the bar, is called the shadow, plus some local terms, some delta functions that are familiar from flat space. Now, the scaling dimensions can either be complex if the field is heavy, or they can be real valued if if your field is light. Now, in lieu of the mass, I will, as is conventional, refer to this parameter nu occasionally. Now, if you exchange such a free field, then, as is well known, its 3-point function exhibits oscillations, where the frequency of these oscillations is because of the mass. So it's the frequency is set by the mass of the particle. So here I'm assuming a sufficiently heavy particle, and these oscillations are due to these power laws that we saw in the 2-point function, where those power laws in position and time get imprinted into inflationary into oscillations in momenta of the inflationary 3-point function. So this is known as the particle production signal, or cosmological collider signal, for instance. And moreover, there's also these analytic terms which arose because of local terms in your position space propagator, where these local terms are entirely mimicable by self-interactions of the inflaton. Now, since I'm asking about light axions, if I tune the mass of this kind of exchange process to 0, which is to say delta to 0, then I produce what is known as the local shape. The dominant exponent is just exactly 0. And then, okay, I can ask, is this what an axion, this is the shape that I should expect to see if I have a spectator axion? And the answer is no. And the way we can try and address that is because by studying the 2-point function of master scalar fields. So if I, so first let's remind ourselves, like if I study the 2-point function of a massless scalar in flat space, its 2-point function decays with distance. But in de Sitter, the same is not true. Its 2-point function actually grows logarithmically with distance. And this is just the position space way of saying something we're familiar with, which is that the modes of master scalar fields freeze out as they exit the horizon, as opposed to decaying. This means that this operator phi is actually, for a master scalar, is not a good operator to work with. It infects your perturbation theory in a way that will show more precisely later on. But moreover, since we're talking about an axion, phi is not even an operator which respects the periodicity of an axion. So it's not a gauge invariant operator in that sense. But what is a gauge invariant operator is e to the I phi, or vertex operators. And such operators, or operators built out of vertex operators, do exhibit healthy behavior. So for instance, the 2-point function of this operator is going to decay with distance, as opposed to grow. And the decay rate is set by your by the two available scales you have in the problem, which is the h and f. So notice that they're highly composite, that these operators are highly composite, and therefore their scaling at long distances is something that cannot be mimicked by any free field, which is to say this beta can be a small number, but it can also be large. If it's small, of course, then it's similar to, then its behavior is more and more similar to um, uh, uh, the behavior of a free field, but this number is only small when f is much larger than h, which is to say the circumference is so large that physics indicator doesn't really care about the periodicity. But this number can also be order 1. It can also be large, in which case physics does care about its periodicity, and this is reflected in the 2-point function that we see. Another manifestation is that these operators don't Wick factorize the way free fields do, which again suggests that the fact that we have to work with these operators, that we're forced to work with these operators, means that the axion sector is strongly coupled. Now, if now I want to exchange, so now we've established that the operator I should really think about exchanging is one of these vertex operators. So I will couple it to the inflaton using some vanilla interaction, because this is a toy example. Now, specific operator, I will just pick a cosine, which is the sum of these vertex operators. And okay, before talking about anything else, I should specify that I will pick the cutoff. We have to talk about the cutoff of the theory. So you might naively think that the cutoff is set by f, but it's actually not quite true. An easy way to see this is that the UV state, you just ask what are the UV states, and those are either KK modes or strings, and those two scales are actually flexible. So the ratio h over f doesn't actually have to be small, it can be order 1 as well. But the cost of making it order 1 is that the coupling to the inflaton needs to be exponentially suppressed in the tension over f squared. So if f is too small, then the coupling will also be too small. But there's a nice EFT way of seeing this this argument. You can ask me about it later on. Now, okay, now so we've established we're exchanging one of these vertex operators, and this is technically a complicated exercise, because strictly speaking, an exchange of this operator is really an infinite tower of melonic loops of massless scalars, and loops in de Sitter especially are hard to do. So I won't go into too many details, but this is this. But one can employ a trick to do these loops, where you resolve a composite operator into sum over free field exchange diagrams, and each diagram is weighted by the spectral density of this operator. So this is just resolving the operator into its Charlin-Lehmann representation, and essentially all of the messiness of doing the loops gets traded for knowing what the exact spectral density is. Now, fortunately for these vertex operators, the spectral density is exactly calculable. It's some long expression which I won't bore you with, but the essential feature is that the spectral density have certain poles, and the locations of these poles exactly encode the long distance behavior of your 2-point function, and in turn it also encodes the exact propagator, the exact correlator as well. So one can determine the correlator, and schematically it's a competition between two terms. One, which is this non-analytic scaling set by the ratio beta, and a local term, which is always analytic. So beta equals 2 is some threshold, and for beta larger than 2, uh, the, the bispectrum looks effectively like a self-interaction of the inflaton. But for beta smaller than 2, it can acquire different shapes. Okay, now I can ask what happens if I ignore the periodicity and I only work with the leading term of a cosine. Even then, the spectral density is knowable, so one can do this loop. And there's only one pole that's relevant in this exchange diagram. And okay, over here, as you can see, the answer you get is infrared is infrared divergent. It's enhanced in the mass of the particle, but I've just given it a small mass to regulate this divergence. But you can see you get a totally different exponent, and you get a highly enhanced amplitude. And this amplitude is completely spurious. It's only occurred because we took the leading term of the cosine and not any of the subleading terms. And moreover, the exponent that we get from this approximation is completely off. If you like, you can also work with a different regulator and obtain the same kind of spurious infrared enhancement. So for instance, if you account for the end of inflation, then this infrared enhancement is captured by the number of e-folds that this axion spends random walking outside the horizon. So this is just to emphasize that if you ignore the periodicity of the axion, then you can totally miss the essential physics of the inflationary correlator it produces. Now, just to summarize, when you had just to recap all that happened, if you have a free field exchange diagram, exchange process like this, then qualitatively it's the shape of the bispectrum breaks down into this analytic piece, which is polynomially suppressed in the mass, and some exponentially suppressed piece, which is non-analytic in its dependence on momentum. Specifically, this exponential suppression is often phrased as a Boltzmann suppression, because you produced a particle as if you produced a particle in a thermal bath. So the cost of producing it is a Boltzmann factor, where sometimes people may write this as in terms of the de Sitter temperature. Now, one can also express this exchange process for axions in a similar fashion, where of course you have these interesting scalings and these interesting exponents, which are set by a different ratio altogether, h over f, but also the overall amplitude, as I mentioned, is going to be suppressed by the string tension divided by Hubble squared. So in this case, it's as if you're exchanging a string which has some effective tension set by beta times your UV string tension. So it's as if you're exchanging really an extended object rather than a point particle. Okay. So just to summarize, I've argued that the strong infrared fluctuations of light scalars in de Sitter really make it necessary to work with operators that respect the periodicity. So it makes physics sensitive to the compactness of field space. Of course, one can always take this toy model and make it more realistic. It would be super interesting to study what kind of shapes you get as a consequence, and maybe even to constrain them using real data. Thank you so much for your attention.